Do you think I'm ready?
On the money for this thing that you need. So if you put, work already with light, then we collect.
I cannot use laser point against it. No, but I will. Yeah. Okay. So what I wanted to say is that my motivation for visiting this university was because I was involved for quite a few years, from 2006, in optical super oscillations. And well, obviously, this is a Center for Super Oscillation Research internationally, and this is why I was very keen to visit here. And then when Daniela kindly invited me, I was very happy with that. So what I wanted to talk today to you about is actually has very little to do to super oscillations. And this is a topic which in my, I would say, groups, we pursue quite intensely for the last 1.5 years. So this is about active matter. And I hope this will have a general interest. So I will okay, this doesn't work. Just a second. I want to present this view, but I can survive without it. Okay, so this is the title of my talk, and it is about a new technology which I believe may emerge, and this is at a very early stage, from the idea of active matter and time crystals. And I believe you haven't heard about that at all. It's really quite a new topic altogether. I will take my instrument for flipping slides. Right, and I will explain in a second why this picture of a gazelle and a wild cat running in the field, why it is relevant to the talk. First of all, I wanted to say that what we are doing here, and actually including super oscillation work, which we are doing, I would like to picture as a field of picophotonics. I guess many of you have heard about nanophotonics when we're interested in the interaction of light with nanostructures. But I'm also interested in more and more so on events and objects in the picometer scale and interaction of light with them. And just to give you the right perception of size, silicon atom is 300 picometers, right? So we're talking really about deeply subwavelength phenomena in optics. But they are, in general, surprisingly easy to see optically, in spite of this thousands times or 10,000 times difference between picometer scale and optical wavelength scale. So this is a very simple example. You make an array of nanowires, and you simply study transmission of this array. And you can imagine that this nanowires suffer Brownian motion, thermal motion. At room temperature, this thermal motion is at amplitude of about 100 picometers. So 1/3 of atomic diameter. But nevertheless, you can see the transmission spectrum of light passing through has resonances at the fundamental frequencies of out-of-plane motion of the nanowires. It's a thermal effect, but you can very easily see evidence of picometric motion. Another example, which is similar, but looking at it from the other side, from the other side, is a situation where you have a nanowire again. Yeah, it doesn't show here. No. A nanowire again. And you send on the nanowire a structured beam. So I would like to call it super oscillatory light beam. And it then scatters on the nanowire, and you detect the scattering pattern. It's a long and interesting story in my view, but essentially, if you train your photodetector, your photosensitive array, to various positions of the nanowire, which you knew about in advance, you then can create a mechanism, an instrument which detect position of the unknown position of the nanowire. The point here is not how it works, but what it gives. It allows you to measure position of the nanowire with respect to the sample with resolution, say, 30 picometers, so 10% of atomic diameter. And this is another example of picophotonics. But now I'm coming to the topic of my talk. So I'm not a technologist, I'm not an engineer, but I would like to project sort of generally where what I'm talking about may lead to. Well, this is electronics, and we all know about electronics. And electronics, obviously, is information technology where information carrier is electric current, right? Maybe current, maybe voltage, but electric current. So in photonics, which is no less important information technology, information carrier is light. Maybe intensity of light, polarization state of light, frequency of light, light. So what my talk will be focused on in a possibility of a technology in which information carrier is a state of movement. And we are talking here about movements at picometer and nanometer scale, typically oscillations of very small nanoscale objects. So this is an emerging technology, and we recently, with my colleague, branded is Timetronics, right? And what I'm going to show you is from what direction one can enter the field of Timetronics, and what is possible and what are advantages and disadvantages of this information technology. So to start with, I will show you with my recent attempt to understand the original, to find original papers on the topic which is called active matter. This is the terminology of active matter, very widely used in biology, in population dynamics, in chemistry for the last, say, I don't know, very intensely for the last 5 years. So here's an example of active matter, which you can see I defined it here as a non-equilibrium matter. This is very important, which converts source of energy into work, typically into motion. So this is a Petri dish with water. In this Petri dish, there's a little boat. And pretend you will then put into this boat a drop of camphor. And this boat starts to move. And this movement is driven by non-equilibrium distribution of camphor and therefore by surface tension. And it will be running that until the system will become equilibrium with respect to surface tension. So this is an incredible example, which if you have a broader view on that, may lead in biology, chemistry, social scientists to many interesting effects, emergent behavior, pattern formation, self-oscillations, waves, phase transitions. What I was able to find that the first description of this floating boat was done in 1888 by a Frenchman, a very, very, very actually clever description of that in the journal which was called La Nature, which actually has nothing to do with nature. This journal died and the Nature journal was formed. So this immediately brings me to the idea of time crystals, which was first proposed, floated, I would rather say, by Frank Wilczek. Frank was and is a famous theorist in the field of particles, and he received Nobel Prize for asymptotic freedom. Allegedly, actually, I heard it from him that he was talking to his wife over dinner, and he said, "Oh, well, look, if we have a situation when unstructured matter may become structured as a result of spontaneous transition forming a crystal, which is periodically in space system." Well, there's a considerable belief that the laws of physics are space-time dual. And through the duality, we shall think that there might be a situation where, as a result of spontaneous organization in time, the system starts to oscillate in time. And he said that perhaps this could happen in the ground state of the system, and published it in 2012, two papers, one about quantum time crystal, he called it time crystal, and about a classical time crystal. Frank is a great man, but he sort of perhaps didn't realize at the beginning that he is suggesting a perpetuum mobile, right? And within a space of 1.5 years, there were a few papers in physics published by various groups saying, well, this is not possible in the ground state. The quantum system cannot oscillate continuously. However, the idea of spontaneous transition to an oscillating state survived, but not for closed system, but for open system. For instance, a system in the presence of light or any other source of energy, and the topic developed. And Frank wasn't still very much engaged in this topic. And I think Daniela may be pleased, we are having in July a conference in Chitraro on time crystals. So a current running definition, I try to put it in my words, a time crystal is a state of matter, very much the same as as liquid, gas, or solid, or plasma. Is a state of matter which is where many body interactions leads to spontaneous mobilization transition to the robust state of oscillation, breaking time translation symmetry under infinitely small change of external influences, and even maybe a quantum measurement, some people say. Once this this work started in 2012, there were a few groups, about 7 groups, which start to finding system in nature which may be behaving as time crystals. There are 2 types of time crystals. The first one is so-called discrete time crystal, where external force which initiates this transition is an oscillating force at frequency 2 omega, and it creates an oscillating system at a frequency omega. And those who are involved in electronics and optics immediately say, oh, well, this is a parametric process. And it is, right? But this community which initiated that sort of did not think about that. So this is a trivial thing. Less trivial thing is a so-called continuous time crystal. So this system is time independent. The force is time independent, but overreaching some threshold value of external force, the system starts to oscillate. So I will show in my slides that for being a time crystal, to qualify the time crystal, so this system should break continuous time translation symmetry. And for that matter, this is called continuous time crystals, sort of similar to original Wilczek idea, and these are called discrete time crystals because they break time translation symmetry discretely. Right. So the essence of my talk is that in the last 2 years, we realized that there is an incredibly, at least in my view, incredibly important mechanism which does lead to time crystals. And this mechanism is a mechanism of non-reciprocal interactions. Those of you who are engaged in electromagnetism optics may think that I'm talking about non-reciprocal electrodynamics. I'm not. So everything I will be talking about is fully within the frame of Lorentz and my time lemmas. So this is non-reciprocal electrodynamics. I'm talking about mechanical interactions, which are non-reciprocal. And I will comment on what it means in a second. So this is something which actually in nature, and I will be doing references to nature many times, is very, very often present. This is you remember the gazelle and the tiger? This is another example of a predator-prey interaction. And it is very well known in population dynamics that there are a lot of predators, a lot of prey. Predators consume most of the prey, population of prey goes down, and then very soon population of predators go down, and then it go up, and this oscillation happens. And this is called Volterra dynamics of predator-prey population. Another example of non-reciprocal interaction is interaction in a flock of birds. You know that flock of birds very often forms very beautiful evolving structures in sky if the weather is good. And to a great extent, this is underpinned by a very trivial fact. There are two birds, A and B. B flies, it doesn't see the A bird. But the A bird sees the bird B and behaves accordingly to the behavior of bird B. This is non-reciprocal interaction. And this is dynamics of this flying of birds is very much controlled by them. There was a video which shows interaction of dissimilar, actually antagonistic organisms or in a petri dish. And as a result of that, sort of they fight between them, creating beautiful patterns like this flower pattern. And this is another example how dissimilar organism in interaction, in asymmetric interaction, can create a system of high order and high beauty. Another example is a human orchestra. There was a very nice Israeli paper when they studied interaction in the string orchestra. You see that all the players do not see each other, but they may be connected through a central console to interact with one another. And this was a very systematic study, which of course revealed that one of the mechanisms of proper synchronization of an orchestra is that a less experienced, a younger player would follow more experienced, more established player. And this is a mechanism of synchronization of the orchestra, one of them. Chinese, this is Chinese paper, we are more interested in dynamics of mass in the presence of an officer. So there's an officer, white, and the mass is addressed in black. And with proper relationship between the officer and the commoner here, the officer can control dynamics of the group. In the case of emergency, very, very efficiently. And this shows how he managed to put all of them on one side of the room, which is not as dangerous as the other. So this is, again, an example of non-reciprocal interaction. And the non-reciprocity here is with a broad term. So in chemistry, pretend you have a Janus particle in which there are two surfaces, two different surfaces, and with different chemistry with respect to the liquid where these particles are suspended. And this may lead to a reaction on that side, and this propel dynamics like in my little boat, but slightly different mechanism. Interestingly, that if you make a mixture of two type dissimilar particles with dissimilar surface chemistry, they will start creating beautiful patterns in the suspension and self-organizing and oscillating everything. And now there's a big topic in the biological community, by chemistry rather, is that this sort of non-reciprocal interactions in the initial bullion of molecules could have been a very important mechanism of matter to life transition at the earlier stages. And I give you another example, which is relevant to mechanics, but also to life and matter transition. So pretend you have a mechanical molecule, which has the following property. It consists of two platforms, which are connected by a spring. So the spring wants to collapse the platform into another platform. But they also run propellants. And as a result of that, when the molecule collapses, it also rotates, right? You may see that this is a very exotic thing. It is, but it's actually maybe found in nature. And embryons of some fish actually have this property. And I will now show what happens if you leave suspension of fish embryos for some time. And you see that they coagulate in an island. But this is important, of course, but considerably more important is that the island starts to rotate, meaning that left-right symmetry is spontaneously broken. And this is immediately sort of induces thinking about life and chirality. In electronics, this is also a very well-known situation where you can have, for instance, a network which has non-reciprocal circulators, so you have some connections between LC circuits which have non-reciprocal meaning, and this sort of starts to generate. So this is therefore my point here is this is non-reciprocal interactions are very often in nature and actually very, very important. So I would now start talking about non-reciprocal optomechanical interaction, because at the end of the day, I want to bring these interactions and the underpinning mechanism of time crystals, which might be important. So this is a very simple example of mechanics. So these are two oscillators. So think of two strings, right, which are somehow connected. So these are linear oscillators. There's no nonlinearity in the system at all. But there's a coupling between them. So the zeta coefficient introduce a term that's proportional to mutual displacement of the oscillators. And of course, everybody knows what happens as a result of that. So if you plot here eigen frequencies of the system, where coupling is 0 here, so we have some split of the eigen frequencies because the initial frequencies in the system are slightly different. But once you increase the coupling, this trajectory run away, and the splitting between eigenfrequencies of the system increases, right? This is a very well known thing. It's considerably less known, but similarly trivial, is that if you assume that the coupling is non-reciprocal, this is simply changing this plus here to a minus there. The situation becomes different. So if the coupling initially was large, excuse me, was small, with increase of coupling, the eigenfrequency collapse, there will be Hopf bifurcation, exceptional points, and the frequency will degenerate. If you look into imaginary part of the frequencies, so one goes up, another goes down, meaning that upon reaching a threshold value, one of the frequencies will win and another oscillation will disappear and system starts to generate. What you need for that, you need two oscillators, two strings in this case, which are non-reciprocally coupled. So this is a simple computational illustration of that. This is one oscillator, this is another oscillator. And just to show them moving somehow, I introduced it here to thermal sources, delta correlated noise here. And you can, I now start increasing the coupling coefficient zeta, and I see what happens with the spectrum of this oscillation. So in the initial state when the system is truly thermal driven, so you have two peaks corresponding to slightly different frequencies of oscillator. I now increase the frequency, and as I said, with increase of the coupling, these two peaks run away one from another. Nothing else of importance happens. However, if I have non-reciprocal coupling, something very, very different happens. So you see, with increase of coupling, it starts to move together. This is important, but really seriously important that upon reaching threshold, the system dramatically increases amplitude of oscillation and relative noise disappears. Noise disappears. So the system becomes very, very clean, oscillating on a single frequency, which is somewhere in between this and that frequency. This is computational result. And if you look at the phase portrait of the system, so I will show you this first. In the thermal state, or state where coupling is reciprocal, this trajectories of each of the oscillators move in a random fashion. They're similar in frequencies. So you see that one may run over another one, but it takes time. In a synchronized state, in a synchronized state of corresponding to non-reciprocal coupling, oscillators are very much synchronized. And if you look at the strings in the synchronized state, in the thermal state, they move like that. But in the synchronized state, they move like that. So the phases are actually antiphases. So, well, a very obvious question, what determines the synchronization process? What is the critical value of coupling, which is needed to synchronize the system? And that is this diagram which shows the very obvious fact that the smaller the dissipation, the lower is requirements for synchronization, and the smaller is the initial difference between frequencies of the nanowires, the easier to synchronize them. And this simple algebra shows that as a result of transition to the mobilized state, to the states of these big oscillations, two oscillators become looking like absolutely identical things. There's no distinction between them, apart that they are oscillating in antiphase. Right, and this is the last slide where I would like to illustrate it further, and this has importance. So now there are not two oscillators, but six, right? And they are distributed in frequency. So these vertical lines corresponds to initial random distribution of frequencies in a relatively small range of frequencies. But they are non-reciprocally coupled. So I now run coupling coefficient, it increases, and you will see upon reaching threshold, the same thing happens. They are all now oscillating on the same frequency. This has important physical implication. So this is exactly the same presented in the following way. These are initial frequency of oscillations. This is coupling coefficient. And you can see when you reach certain coupling value, the frequencies merge, then another come, then they merge, then come again. But eventually, upon reaching the threshold value, they become oscillating in a single frequency. And if you then run it, the story in opposite direction, so there will be hysteresis. Importantly, that a system which is having a rich number of trajectories, in this case, 6 different oscillators, eventually collapses to a system with a single frequency. And in thermodynamics, this is an example of ergodicity collapse. I will show you this in a second. This is a very simple cartoon explaining what is ergodicity breaking. So think this is a system, and this is a phase trajectory in the system, which can work in such a way that if you wait for long time enough, every point in the phase portrait of the system will be visited. And this is meaning that the system is ergodic. And the anergodic system is where certain frequencies, certain trajectories cannot be reached, even if you wait for a long time. And in classical thermodynamics, it is very well known that it is not possible to convert one ergodic system into a non-ergodic system. So you know the concept of Maxwell demon is a typical example of that. But generally, this is in classical thermodynamics, this is not a possible process. So here comes an example that what is not possible in physics is actually very much possible in life. So this is an example of a can containing sugar solution. And there's a funnel with little hole here, and there's a room, and there's a fly in the room. And you know, of course, that upon waiting for some time, all the flies will find their way to the can because they're attracted to sugar vapors. But the atoms of air still will have the same density outside and inside the can. So the system apparently breaks ergodicity. And ergodicity is actually very often broken in living system. So that example, which I just demonstrated on synchronization of oscillators, has a feature which we often observe in nature, but very rarely observed in deterministic physical systems. Can light induce non-reciprocal interactions? Again, I'm not talking about electromagnetic reciprocity, I'm talking about action and reaction forces. Now come to the Newtonian dynamics. So I give you an example that it can, and it's a very simple example. So light coming from the top and hitting a nanoparticle. And as a result of that, nanoparticle will see a light pressure force. So if I now introduce another particle in between, the light source of the particle, this is particle 2, the amount of light coming through will be reduced by reflection from this particle. And therefore, particle 2 exerts a force on particle 1, which is going up, right? Nothing special. Until you look at a situation, what happens with particle 2. So particle 2 is pushed by light in the down direction, but particle 1 is capable of reflecting some light and pushing particle 2 up. So therefore, there will be a force exerted by particle 1 on particle 2. And and this force is also looking up. So this one is looking up, one acting on 2 up, 2 acting on 1 also up. And Newtonian third law tells us that they should be equal but opposite into direction. So these two forces are in the same direction. I can give you a number of examples of that, but this is particle scattering is the best example. Why this is possible to happen, I will say in a second, but before I will show you something much better calculated. So you perhaps you will trust me more. So these are 2 particles again, light coming from the top. And I am plotting here action of mutual interaction of particle forces. So when the system is like that, and the wavefront coming top from the top, so the Newton third law holds perfectly well. So the action and reaction are equal and opposite direction. But should you make the particle different, and this is very important, you need to operate with dissimilar objects. The third Newtonian law is immediately broken. And the reason for that is very simple. The third law of Newton is established and derived and for closed systems. When a system is in the presence of another source of energy, like light, that the Newtonian law simply is not applicable there. So, and in the presence of external field, we can see numerous examples of non-reciprocal interactions. So so this is a trivial fact, but I think that in 2014, I, with my colleagues, for the first time pinpointed that in a little paper in optics letters, and then a more rigorous analysis of this was undertaken, well, 10 years ago for the first time. And non-reciprocal interactions in presence of light was clearly understood. It happens that it needed 10 years for a group to show this experimentally. And it was shown last year and in 2022 as well, that two particles trapped in optical traps actually can be manipulated with light to show non-reciprocal dynamics, exactly as in these oscillator equations which I told you about. Okay, so I will may perhaps skip that, but briefly. So this is an example of more complex particles interacting. So this is an ensemble of split ring and a split ring. If you send light through a material made out of the structures in one direction and in the opposite direction, exactly in accordance with Lorentz reciprocity, the transmission coefficient and retardation of the electromagnetic wave will be the same. However, the interactions between them, between these two particles, will depend whether you go from here with light or from there, and this interaction will have very strong non-reciprocal component. Okay, can we have a good use of these interactions in time crystals? And this is a specialty of our work. We essentially realized that this might be a remarkable opportunity to create a time crystal matter, not in exotic quantum system, which it has been demonstrated before us, like Rydberg atoms or cold atoms or spin systems or magnons, but in a very practical situation where time crystal matter may be created in a robust situation using nanotechnology approach and in a very similar way as any electronics optical circuits are created. So let me show you how this is possible. So our system, sort of our prototype system we are working all the time, is again two nanowires here, which are strings, right? And the important thing here, but they are dissimilar. So this one is slightly wider, this is slightly narrow, but it's not important. What's important is they're decorated with resonators. In this case of this picture, it is a plasmonic resonator. So then if you take these plasmonic resonators and engineer them correctly and pick up a correct wavelength of light, you may engage non-reciprocal interaction between them. And you even can make situation where non-reciprocal interaction will be dominant, if not only interaction at this wavelength of light. So these two oscillators starts to move together. These are systems which we work with. These are nanowires decorated with plasmonic particles. These are nanowires decorated with little blocks, bricks of amorphous silicon. This is something else, but a very characteristic feature that these arrays of oscillators are made of dissimilar pairs. And this dissimilarity is provision for them to be able to interact non-reciprocally at a certain wavelength. So all these examples are time crystals. When you send light on it, they move from the state of very thermal uncorrelated oscillations at a very small amplitude to the state of very intense oscillations like that, coherent across the entire array. But most importantly, it is a material. So this is a material which is time crystal. So what I'm really saying is that if this lady makes it in a clean room, she can give it to a researcher who will study it and put it into a device of interest. I can give you our samples to study. So, but let me just show what this actually samples do. I may skip this slide. This shows how actually to optimize this little decorating resonators to show strong non-reciprocal behavior when they are illuminated with light. This is how it works in our lab in particular. So these are, in a way, very simple experiment. You put time crystals here, you see transmission through the sample. Samples are small. We're talking about 10 by 10 microns in size. and containing anything between a few oscillators to 100 oscillators roughly. Right? This is exactly the same, but now the sample is placed in a helium cryostat, so one can study the role of thermal noise in the system, so the Brownian motion effects. But it is very, for optical scientists, it's a very common situation. This is simply a fiber network with detectors, modulators, sources, and the time crystal is integrated in the fiber network. So this is now, I will not show any computational results now. I only show you examples of experimental observation. So we have this structure, which is a silicon membrane, 100 nanometers thick. It's cut into nanowires. Nanowires are decorated with amorphous silicon blocks, making them dissimilar pairs. And this about 25 of them in the array. You illuminate it with light, and only thing you watch is what is the transmission of the sample. So these lines show intensity of light, which is illuminated, right? Which used to illuminate, so it goes up, stabilizes, goes down. Once you get with intensity of light to roughly this point, you see that the oscillation starts to synchronize, and from here it gets to exponential process of growth, and then stabilizes with amplitude. The difference between amplitude here and amplitude there is 5 orders of magnitude. So random noise become very large oscillation. If you switch off the light, the system desynchronizes. Essentially, it comes to the initial thermal state. These are experimental diagrams of what happens within this interval of time. So from here to there, so in a space of few fractions of milliseconds. So you started from this point, and the system starts winding up, and then reach this stable final phase trajectory, which is presented here, and then desynchronize when you switch off the light. So this is a demonstration of a time crystal behavior. So this time crystal behavior, this is just zooming into this experimental phase trajectories in the system. So a bit more details. I now repeat this cycle, intensity up, intensity down several times, right? And what I watch now is the entropy, the spectral entropy of motion, essentially how ordered the motion is. It's if you know the time trace, it's very easy to calculate entropy. Most important thing is here. Once oscillation synchronizes, the entropy drops down. So we have a local decrease of entropy in the system upon synchronization, as you would expect. But this is, again, another example of behavior which we often see in living systems, in particular that example which I gave before. So the creation of patterns is local reduction of entropy. And here we have a material which drops local entropy during the synchronization process. Of course, global entropy goes up all the time because you have a source of energy, but the system itself shows local entropy decrease. Another interesting feature, so this is again intensity of light, and this is frequency at which the system oscillates. So this horizontal line indicates that once the synchronization happens, the system gets robust oscillation frequency, which is actually very difficult to change. So I will say this in a second. This is, again, absolutely the same with plasmonic system and exactly the same synchronization and mobilization trajectories. The system, very different optically. It's now a plasmonic system, but shows a very similar behavior. So this is an attempt to, not an attempt, it's simply computational illustration of the same fact. Again, thermal state, mobilization state, mobilized state, demobilization, depending on the intensity of light falling on the array. Well, one might be very interested in see how robust this oscillation, so this frequency of oscillation this time, how robust this frequency is, and we were obviously curious about that. What we did, we tried to modulate the laser pump, which creates synchronization. And of course, if you modulate this very strongly, you may reduce the intensity range in which it's stabilized. But what is very important is that the frequency at which system stabilizes remains the same. So once the time crystal state is reached, it starts it is becoming very, very stable. And the reason for that is, and this is a very, very important point, is that upon reaching the time crystal state, the work done by light on the time crystal becomes zero. So if you want to think about that in more common terms, so think of a thermal state as an orchestra where different players playing different thermal random music, right? Upon sending light on the system, all of a sudden they start playing on the same instrument, the same single tone, right? And much, 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 much louder. And this is accompanied, as I said, by ergodicity breaking and local entropy decrease. I just simply showing again the quotation from Frank Wilczek, which is related to the time crystal as a necessity breaking time translation symmetry. And I will explain this in a second. I will drop this. I will come immediately to the time translation symmetry. Pretend time translation symmetry has nothing to do with time reversal. Right? Time translation symmetry is the following. I do experiment today, or tomorrow, or in a year time, and the results are the same. So if you do experiments which involve the time crystal, and you do it today and tomorrow and the next time, and the result is the same, this is not a time crystal. The time crystal shall break time translation symmetry continuously. And it means that every time you kickstart the time crystal state, so this is intensity of light which sort of triggers the time crystal oscillation. The phase of the resulting oscillation shall not be the same. It shall actually be random. And if this phase is random, meaning that if you do experiment today, if we all involve in time crystal, and tomorrow, you don't expect the same result. And this randomness is a fundamental feature of time crystal math. And we, of course, were very keen to understand whether time crystals we are working with are capable of showing this continuous breakage of the time translation symmetry. So I will show you this on the next slide. I will skip. Yeah. So here we plot time, and these vertical bars illustrate sort of experiment number 1, number 2, number 3, number 25. So and height of the bar is observed phase of oscillations from the moment oscillation was triggered. And you see that they wobble around between 0 phase and 2 pi. And in order to show that this is a random sequence, one needs to do a lot of mathematical tests. And these tests involve quantifying unpredictability of fluctuations, how distributed the phases are between 0 and 2 pi, and many other tests. So there, in total, I didn't list them all. These are typically people who claim random number generated will need to do 6 tests. And we have done this test on our system. You know, when you talk about randomness, you cannot say my system give random numbers. If you do finite time experiment, you need infinite time to claim that. But if you have in your disposal only finite amount of time, there are some tolerances related to the final number of time. And this is how all physical and mathematical number generators, random number generators are constructed. So I want to say a simple thing. A random number generator based on time crystal is as good and slightly better than random number generators used in MATLAB. So it's a very good one. Okay. This is if I spend more time explaining that. Okay, so now I come to this slide, which is about time translation symmetry. Fundamental laws of physics are generally, well, I'm using exact quotation from one version, are generally question mark, obey time translation symmetry. And the best example, the best illustration of that in physics is that if you observe a spectrum of hydrogen discharge in on the Earth and in the remote galaxies, you will see that also spectra in remote galaxies are Doppler shifted because the further away galaxy is, the higher the speed it travels. So nevertheless, the spectra are exactly the same, right? So meaning that the spectra created the sort of multi-billions times years ago would have the same physics law as now and today on Earth. It is physics, but you already see my next slide. But in life, this doesn't work like that. The life does not obey time translation symmetry. What you were able to do in 10 years old and 90 years old is quite different, right? So, but the time crystal I just demonstrated to you seems to be having this property of not obeying time translation symmetry. It is broken. I already gave you the example of ergodicity, which is broken again, very similar to biological systems. And of course, entropy is a trivial example. We all know that entropy globally goes. I do not dispute that, but locally, organization in time crystals, like organization in nature, can reduce the entropy in the system. Okay, so let me now show you Timetronics. So this will be the last slide, last couple of slides. So what we are envisaging is the development of data processing technology, which is based on the idea of Timetronics. And Timetronics has a elementary building blocks, which is a timetron, right? So like think about transistor for electronics, but timetron. And timetron may have several inputs, several outputs. Well, in my vision, it's easier to do with optics. So you think about optical input and optical output. And what you do here, if you switch this system from the state of non-motion or of the thermal motion to the state of synchronized, mobilized motion at high amplitude. So this is the whole process of Timetronics, to switch on and to switch off and to control this in a timetron. And you may think about timetron as a little block, which there's a network of them connected somehow, or you may think of that as a large array of oscillators, which may be two-dimensional array, and interconnect with them happens through boundaries between the domains of these arrays and things like that. It doesn't matter, the idea is the same. Now, two most important things. When the system is a ground state, so thermal oscillation, so it does not consume any energy whatsoever because it's thermal equilibrium with the environment. When you want to switch it to the mobilized state, you must spend energy. And this energy is roughly the Gu constant x squared, where x is amplitude of oscillations over the two. So, and this is how much energy you need to spend. And if you take examples of the experimental work, which I just presented to you, we go from sub 100 picometer motion to about 10 nanometer oscillations. So this energy is roughly 10 minus 16 joule. So the energy which is needed to switch a flip-flop in this computer is 10 minus 12, 10 minus 11 joule. So this is a 5 fixed 4 orders of magnitude smaller. It is only first good news. The second good news, once you reach the mobilized state, you still need to have a presence of light which maintains the time crystal. But the light doesn't do work on the time crystal anymore. So this upper state is supported at no expense of energy. And you may start thinking of how to make a technology out of there, how to connect them, how to organize various architectures, neural networks, several automata machines, and simply Boolean logic operations. And this is what we are doing now. So what we have done so far, and I skipped that because I think it may be more interesting to the engineering community. We have demonstrated the random number generator, optical frequency mixer, flip-flop, and optical Schmidt trigger. Optical Schmidt trigger is in fact very, very important device, which is actually currently absent in the photonic technology. So you cannot make all optical data processing and optical networks because you do not have Schmidt trigger, and for that matter, you cannot make various logical elements truly optical. So the challenges here are present. First of all, we need to go from one-dimensional arrays of oscillators to two-dimensional arrays. For instance, think of, again, they might be dissimilar, right? Think of a chessboard. The black and the white are slightly different oscillators. And we already showed that you can synchronize them, and we are now studying how to make them with useful functionalities. There's an interconnect problem. I will discuss that, and the response time. And here, this is a very, very important moment. So pretend you have a music fork, and you make this music, ding, and you make this music fork out of silicon. And you now reduce the size proportionally of the music fork from centimeters to nanometers. And the ringing tone will increase in frequency. So when you got it to a submicron, it will start oscillating at gigahertz frequencies. And actually, as a function of size, this frequency of oscillation grows up faster than clock speed of Pentium processor. Nanomechanics is actually very fast. And in principle, it is actually faster than electronics, at least made out of standard CMOS technology in silicon. So this is a challenge to go to faster response time, but not a limitation in principle. And the last slide, which I wanted to show you, is this one, is to partially answer the question, how it is possible that you can beat electronics in energy consumption. I give you the following example. Well, I guess all of us lived long enough to remember optical data storage made out of phase change materials. So how optical data storage works? It works in the following way. So you have a crystal, you send some stimulus, maybe optical, maybe electronic current. As a result of that, the crystal become amorphous. And as a result of that, the optical properties of the amorphous system change. So you then can have it in optical disk. You can recognize the element of bit which is amorphous or crystalline and store information this way. But you need to have a strong change of optical properties, right? So if you do it through change of the crystal lattice, a very rude and but nevertheless correct estimate of how much energy you need to supply is very simple. You change the phononic structure in the system. So it is typically one phonon per atom. But if you would like to change optical properties of the system by acting on its electronic system, so for instance, for example, strong nonlinearity may be achieved if you saturate absorption in the system, in a two-level system. So then you need to spend roughly 1 photon per atom. And there's a 4 orders of magnitude difference between phonon and photon, and the result is the same, you change optical property. And this is somewhat similar to Timetronics. So you start with a system which is like that, you engage it into emotion, right? And as a result of that, the optical properties of the system changes. And again, the energy required for that is energy necessary to operate on the photonic system of the crystal rather than onto the optical. Okay, I finished that, and I just wanted to show you that the resulting slide. I will keep all these details, but the important thing, the time crystal seems to be having functionalities not available in conventional materials, and intriguingly resembling functionalities which are available in nature. And this is the end of my presentation. So this is how ChatGPT perceived, asked ChatGPT to tell me how the photonics time crystal laboratory look like, and created that. And these are guys involved in that. This is researchers in Singapore, in Southampton, and my colleagues in Southampton. So that's all. Thank you very much.
Thank you, Nikolay. Any questions, comments? Yeah, Andrew.
So let me start with this non-reciprocal oscillators. You correctly pointed out, as we learned in freshman physics, there is this principle of Newton's third law of motion. For every action, opposite reaction, and from that follows very important principles like conservation of momentum.
Yep.
Right. So can you talk about when you're creating physically these interacting with light? You describe physically what's happening, because you're not really cheating conservation of momentum. You're just storing it somewhere else, right? You're having recoil with your light. So can you talk about, from a physical fundamental point of view, what's going on with this, how you create the non-reciprocal interactions?
Yeah. So I wanted to start with something, but you start with this. So certain rules of physical interactions are explicitly linked to certain conservation laws. And the first publication on that actually came, I always forget the name of this lady who was a German by birth and then came to work in the United States, who wrote a fundamental paper on the relationship between forces and conservation laws. Yeah. So, everybody knows about this paper, but nobody read about it. So, I actually downloaded and read the paper, and she explicitly said that everything is derived in this paper, assumes that there's no non-reciprocal interactions in the system. But coming back to your question directly, so the Newton law is not applicable to open systems, full stop. There's no need to justify anything, why this law is broken, what is the condition of the book. It's simply not applicable. It's only operational for closed systems. And when you have supply of energy, in this case, supply of energy in the form of light, you shall not assume that Newton law works.
But if you include the light in your description, it becomes closed again. Right? So my question is,
this has become, in a way, a three-body system, right? And you know how complex the three-body system analysis is. And there are works, in particular in spintronics, that relate the presence of external source of light treated as a third body, right? If interested, I can give you this example. But yeah, this may be an answer on your question.
yeah. So the point is the momentum is carried by the light, right? It's not as though the momentum is destroyed.
No. The mechanism behind that is very simple. It's simply radiation of light or scattering of light, which change momentum. There's no rocket science there at all.
Yeah, beautiful talk, first of all. I really enjoyed this. It seems like there's a lot of overlap between this and the work of Ilya Prigogine. Is the community of time crystals aware of this work?
Prigozhin, of course. So all the chemists wrote about path information, oscillations, and and all that sort of Prigozhin instabilities. So of course, I'm aware of that. This is, if you wish, in a way, reincarnation of this work in a different
Right.
life.
That's what it seemed like to me. That's why I was curious. Like, it seems like an evolution of that, like now it's more applicable towards engineering.
It actually goes down to synergetics topic in the history of the dynamical systems, right? But I need to say that in Prigozhin's work, certainly as far as I know, non-reciprocal interactions, non-reciprocal mechanical interactions were not considered. You can get organization in the system, self-oscillation through the nonlinearity, which is known the Kuramoto mechanism, right? Kuramoto mechanism of, and this requires nonlinearity in the system. The beauty of system I'm talking about is that it is initially, before presence of light, is a linear system. And this makes the whole dynamics, conditions for organization and oscillations very, very different from Kuramoto and in some way Prigozhin's approach.
Yeah, we can talk more later, but I'd like to explore this. It's a fun connection.
Armin?
Yeah, when you were talking about mobilized state, and you said that no energy is consumed but ain't we coming back to perpetuum mobile paradox there?
No, not at all. So, yeah. I need to be perhaps more explicit here. So the energy, the work which is done by the external field of light is reduced upon synchronization to that extent to which quality factor of the oscillators collapses. And the finite value to which the quality factor collapses, and it remains final, determine that residual amount of energy you need to supply. So this is true. So that's well, I don't think that there's a perpetuum mobile, but very close. You know that Leonardo da Vinci once said he was experimenting with perpetuum mobilis, and he lost trust in that, and he wrote famously something like that: for those who try to do a perpetuum mobile, I would like them to consult people who wants to convert lead into gold.
Any other question from this room? Oh, Roman.
Can you say more about entropy decrease? You mentioned what time there was a local decrease.
Yeah, so what is entropy? It's a measure of order. Here I'm talking about order of oscillation. The system is initially two uncorrelated chaotically moving oscillators. Over a sudden, they start to oscillate synchronously, and no wonder that there's order in the system. So therefore, it's called spectral entropy. Spectral entropy goes down markedly and stabilizes at a low level. So it is not saying that somewhere else entropy was not created. It obviously was as a result of light pushing the synchronization forward.
But if you look at the time crystal as a periodic system, the entropy should just stay constant.
No, it didn't. Well, so again,
If you just go between the two.
I'm talking about only one carrier of entropy, which is oscillation itself, which is measured by entropy of the motion of the how the function of displacement changes in time. It's the same thing. If you look at a petri dish and all of a sudden see formation of a pattern, you see that a system with pretty homogeneous and random spatial spectrum become a system which has certain spectral components. It's the same thing.
Any question from your Armin is another one, sure.
Yeah, if I may, your mobilization and demobilization curves were mainly monotonic, but I think on one of your slides there was non-monotonic demobilization. When does that happen?
Thank you. Demobilization is trivial process. You have in homogeneously broadened system of oscillators, meaning that they all have slightly different systems. When you release them, they go. They start to oscillate, and so the beats between them is one mechanism of relaxation. Another, each of them has a damping constant. And so the combination between damping and beating creates this thing.
Any question from the people on Zoom? I don't hear anything. You have one more question?
Just very simple. Maybe you already answered this in the end. Do you have any particular ideas about the computer storage? This used for the computer storage?
Yes, again, so the computer storage is a flip-flop, right, in elementary. So we have demonstrated a flip-flop. So essentially, it is a very simple thing. One system has a hysteresis, and this system is induced into mobilized state at one intensity and drops into a much lower intensity from stability. So you have a memory element, right? I think that beyond the flip-flop and memory element, so this is a wonderful platform for neural networks. And the beauty for this system is that as far as neural networks are concerned, the robustness of the network is a very important factor. And here, the difference between state 1 and state 0 is a 5 orders of magnitude of energy. So it should be very robust. So we're trying to, I may tell you what we are trying to do. We are trying to create a two-dimensional arrays where are illuminated by structured light. So different elements of the array are illuminated by light of different intensity through a special light modulator, right? And then you read the system by another laser, and then you can engage us into a learning process.
One more practical question. How deep are you cooling your system? How deep are you cooling the system? To which temperatures we need?
It is room temperature, it's all room temperature.
Oh, it's wrong because you don't crash.
Yeah. The cryostat, because we still are very curious of how important is the initial thermal fluctuations of the elements on synchronization. And of course, there is a relation. You can imagine what is that. So if you have more thermal fluctuations, so the time necessary to develop time crystal states becomes shorter and shorter. It's like in any parametric system.
Yes.
Very quick one.
Of course.
You mentioned that the system has to be two-dimensional. Is that a theorem?
No. I said the system has to be consistent of two dissimilar creatures.
No, but when you were showing those arrays, you say the array has to be two-dimensional. Did I misunderstand?
Yeah, you misunderstood me. I said we are working on two-dimensional arrays of oscillators. So you can imagine, for instance, a membrane in which instead of strings oscillating like that, they're flip-flops, little flips. And then they may be connected not to the nearest neighbor, but to 8 nearest neighbor. And the behavior becomes considerably more complex. And density is much higher, of course.
Anything else? No, thank you very much. Zheludev is going to be around today and tomorrow, right?
Yes.
Yeah. So, and I think today we are scheduled